Hi everyone. In this video, I'll present our work on saturation throughput analysis of hybrid access MAC protocol in IEEE 802.11ax WLANs. This is an extended version of our talk at Globecom Conference 2024 in Cape Town, South Africa. As an outline, I'll start with the hybrid access in 802.11ax WLANs and we'll see the analysis of saturation throughput and numerical results. IEEE 802.11ax is the IEEE standard for the current Wi-Fi generation, Wi-Fi 6. Wi-Fi 6 improves capacity and latency in dense deployments. For this, it introduced novel features in both physical layer and medium access control layer. In physical layer, Wi-Fi 6 had introduced orthogonal frequency division multiple access and uplink multi-user multiple output multiple input capabilities. And in the medium access control layer, it had introduced OFDMA-based hybrid access. Hybrid access is a combination of contention-based uplink OFDMA random access and contention-free scheduled access. And our contributions in this work are the analysis of IEEE 802.11ax with hybrid access, where we analyze the random access and saturation scheduled access saturation throughputs. And we characterize the variations in the number of users in random access and scheduled access. This differs from the conventional assumptions where they assume the number of users in scheduled access and random access are constants. In our work, we also incorporate the impact of schedulers and discrete rate adaptation, where we model random and chain-level schedulers. In Wi-Fi, OFDMA divides the channel bandwidth into orthogonal resource units, and these resource units are allocated to different users. The access point manages OFDMA transmissions by transmitting trigger frames. Trigger frame initiates the OFDMA transmissions in uplink and downlink, and it contains the RU allocation for random access and scheduled access and user scheduling information for scheduled access. Now let's look at how hybrid access works in Wi-Fi. The access point allocates the RUs for scheduled access and random access. In scheduled access, the access point schedules the users on the RUs allocated for scheduled access. It is based on the buffer status reports. For example, here the 4 users are having different buffer status reports, which captures their data requirements in uplink. And the access point schedules these users. For example, it schedules the user 2 for 1 TF cycles so that it can transmit the 1 packet. And the users report these buffer status reports to the access point in random access. And they send these BSRs with payload frames. Scheduled access is contention free and it improves throughput. However, the random access enables the users to enter scheduled access. Now let's look at the backup process in random access. Uplink OFDMA random access follows exponential backup based contention mechanism, which is very similar to legacy backup. For this, each random access user uniformly samples a counter from a contention window. So here there are 4 random access users and they sample a counter from a uniform window. And after a user receives a trigger frame which mentions the RUs allocated for random access, it decrements the counter by the number of RUs allocated to random access. So here there are 3 RUs allocated for random access, hence the backup counters are decremented by 3. And as soon as the counters become 0 or negative, the users randomly choose one of the random access RUs and they try to attempt. If only one user is trying to attempt on one RU, there will be a successful transmission. And if there are more users attempting to transmit on a single RU, it will be a collision. And there is a possibility that a RU is chosen by none of the users. All these cases are shown in this figure. After every successful transmission, the contention windows are reset to C min value. And after every collision, the contention window is doubled until it reaches Cmax. This uplink OFDMA random access differs from legacy random access in a couple of ways. One is, in uplink OFDMA random access, the backup counter decrements are trigger based. Only whenever the users receive the trigger frame, which mentions the RUs allocated for random access, the decrement will happen. And the backup counter decrements are equal to number of RUs allocated for random access. So the decrements happen in a bulk number. After successfully transmitting the buffer status reports in random access, the users enter scheduled access and they no longer participate in the random access based contention. They wait in the scheduled access for that so that the access point allocates the scheduled access RUs to the users. And the scheduler determines the user allocation in scheduled access. A user stays in the scheduled access for a random time, which we model as a geometric random variable. After this random time, a user returns to random access to again reports the number of packets using random access. Hence, the users move between random access and scheduled access, which depends on RU allocation and the contention in medium access control layer and the time a user stays in SA. For example, in this figure, we plot the number of users in scheduled access in different trigger frame cycles. Here, the total number of users are equal to 50 and the total number of RUs are 16, where 4 RUs are allocated for random access. As you could see, the number of users in scheduled access varies in the consecutive trigger frame cycle. Hence, the number of users in SA is not a constant number, and we need to model this. With this, let's move to the analysis of saturation throughput. Our analytical approach would be, first we'll start with the analysis of backup process of random access, where we derive the backup parameters for a given number of users in random access. Then we model the evolution of number of users in scheduled access and random access using a discrete time Markov model. We were able to do this Markov model since we consider the time a user stays in SA is a geometric random variable. Then we derive the saturation throughputs in random access and scheduled access. We compute the saturation throughputs in scheduled access for random and max throughput schedulers. To model the backup process in uplink OFDMA random access, we can do the exact modeling using the discrete time Markov chain. However, the success and collision processes are coupled and correlated. Hence, the exact number of states in the Markov chain will be order of k to the power rho, where k is the total number of users and rho is given in this expression. Hence, even for small number of users, there will be a large number of states, which makes the exact analysis intractable. So for tractable analysis, we follow decoupling approximations, which state a number of a user's attempt is independent of the states of all other users. And at each attempt, collision occurs regardless of the number of retransmissions. So with the decoupling approximations, we derive conditional collision probability and attempt rate. We were able to derive the conditional collision probability and attempt rate as fixed point expressions, which are shown here. And these are expressed in terms of each other and system parameters. We also prove a unique fixed point exists and can be found in the interval 0, 1. To compute the attempt rate, we use renewal reward theorem, where we model the number of attempts to transmit a BSR packet successfully in random access as a reward in the backup duration, where the total backup duration is a renewal cycle and the number of attempts in the total backup duration is a reward associated with the renewal cycle. And start of each new BSR packet transmission attempts are renewal instance. So with this, we were able to compute the attempt rate using renewal reward theorem, which is given in these expressions. And we do not impose any cap on the number of retransmission attempts. Hence, we model the number of attempts to transmit a BSR packet using a geometric distribution. So using these, we compute the expression for the attempt rate for a given number of users in random access. For a detailed analysis of these derivations, please look at the conference paper. Now, we model the evolution of number of users in scheduled access and random access using the Markov model. Since we consider a user stays in scheduled access for a geometric time and also from the decoupling approximations, we model this evolution using a discrete time Markov chain. This particular diagram represents the discrete time Markov chain where there are two random access RUs and one scheduled access RU. And a state represents the number of users in scheduled access in TF cycle T. Since there are total K users, we could see the number of scheduled access users changes from 0 to K. Since there are total 2 random access RUs, at max there can be 2 successful BSR transmissions. Hence, the number of users in scheduled access in any TF cycle can increase by 2. And since there is only one scheduled access RU, at max only one SA user can complete its transmission and move to UORA. Hence, we see the number of users in scheduled access are decremented by at max 1. And these transition probabilities are represented in terms of zetas, lambdas, and mu's, where the expressions for are the definitions of these probabilities are given in this block. We compute these probabilities in terms of the attempt rate and system parameters. Let's quickly look at how we construct zeta in this slide. We compute zeta using a polynomial construction. This construction in this slide is shown for 2 UORA users and there are 2 random access RUs. And the coefficient of xt to the power LD captures the probability where there are LD attempts occurring on the dth UORA RU. So when there are 2 UORA users and 2 UORA RUs, if we expand this expression, for example, x1 to the power 2 captures 2 attempts occurring on RU1, which is a collision. And the interest of our model would be a successful transmissions, which will occur when the powers are just 1, right? So the x1 captures there is only one attempt occurring on RU1. x2 captures there is only one attempt occurring on RU2. So adding these two will give probability of one attempts occurring when there are 2 UORA users. Similarly, the coefficient of x1, x2 captures 2 successful transmissions happen when there are 2 UORA RUs. So using these, we compute zeta, n of KRA, and lambda and mu's are represented in terms of zetas and betas. So the detailed expressions are the general polynomial construction for any given number of UORA user and for any n is given in the paper. With this, now we compute the saturation throughputs for random access and scheduled access. So to compute the saturation throughput for random access, first we compute the saturation throughput for a given number of users in random access. Then we average it using the steady state probabilities given by the Markov model. So nu of KRA, NRA captures the success probability of a UORA user when there are KRA UORA users and the NRA UORA RUs. It is given by this expressions which is equal to beta of KRA into 1 minus beta by NRA to the power KRA minus 1. And when we multiply the success probability with KRA, we get the total number of successful UORA users in a TF cycle. And we multiply that with R bar, which is average throughput of a UORA user in discrete rate adaptation. Multiplying this with the TP will give the total number of bits, data bits transmitted in the trigger frame cycle. And we divide this by TH to get the saturation throughput when there are KRA UORA users. And we average this across the number of UORA users using the Markov steady state probabilities. Now let's look at how do we compute the average throughput of a user in discrete rate adaptation. In discrete rate adaptation, if the SNR falls between two thresholds, for example, if we look at the thresholds T1 and T2, if the SNR of the user falls between these two thresholds, then the user will be transmitted with the MCS1 with rate R1. So using this, we compute the average throughput of a user in discrete rate adaptation, which is given by these expressions. In our model, we consider the user channel follows Rayleigh fading. Hence, the channel gain will be an exponential random variable. And the users are around the AP with the inner radius of 1 meter and the outer radius of 50 meters. So the distance of a user is again a random variable which follows a distribution. So using this model or the derivations, we compute the closed form expressions for the discrete rate adaptation average throughput. The steps and the details are given in the paper. Similarly, we compute the saturation throughput for scheduled access for a given number of users in scheduled access and the given number of RUs in scheduled access. Then we average it over the number of users in scheduled access. We derive the scheduled access throughput for random scheduler and channel aware scheduler. The random scheduler In the random scheduler, the AP randomly allocates RUs to the users. For this, we compute the closed form expression, which is given by minimum of KSA, NSA, because at max the access point can schedule only this many number of users in a TF cycle. For a channel aware scheduler, since the scheduling assignment variables are coupled, we compute the expectation uh, using Monte Carlo simulations and store it in a lookup table and use it to compute the scheduled access throughput expression for the channel aware scheduler. Now with this, let's move to the numerical results in hybrid access. This figure shows the simulation results that we use to get the numerical results. In the table, we show the standard specific simulation parameters where we take the bandwidth equal to 160 megahertz, the carrier frequency is equal to 5 gigahertz. This figure shows the random access and scheduled access throughputs as a function of the total number of users for different RU allocation. So in this figure, we plot the throughputs for different RU allocation where we have 2 RUs and 2, 4 and 8 RUs allocated for random access. In both the figures, the lines, solid lines are for the analysis and the markers are simulation. As we could see, the analysis and simulation results match each other well. In both random access and scheduled access throughputs, the throughput increase as the number of users increases. And in the scheduled access, the throughput increase as the number of RUs allocated for scheduled access increases because when the number of RUs increases in scheduled access, the users can have more RUs to randomly choose to transmit. Hence, the success probability in random access increases, hence the scheduled access throughput increases. However, in scheduled access throughput, as the number of RUs for random access increases, we see first the scheduled access throughput increases and then decreases. That is because when NRA is equal to 8, we have only 8 remaining RUs for scheduled access. So even though we have enough users in scheduled access, we have lesser RUs to be allocated for scheduled access. However, in the case of NRA is equal to 2, we have 14 RUs for scheduled access. But since we have only 2 RUs for random access, we have fewer BSR transmissions. Hence, we have very fewer users in scheduled access. This figure shows the red lines are when we do not model the number of users, the variation in the number of users in scheduled access and random access using the Markov chain. And we assume the number of users in scheduled access are always equal to the number of RUs in scheduled access and the rest of the users are in random access. So this validates the need to model the number of users, the variation in the number of users in scheduled access and random access. Now let's look at the impact of schedulers on the total saturation throughput. This figure plots the total saturation throughput as a function of number of users, total number of users for different RU allocation. As we see, the blue curve are for the max throughput scheduler and the black curves are for the random scheduler. Again, the analysis and simulation results match each other well. And for different RU allocations, we see max throughput scheduler achieves higher throughput, and the throughput depends on the number of RUs allocated for random access. And to conclude, in this work, we have analyzed the throughput of IEEE 802.11ax with random access and scheduled access, where we have used decoupling approximations and Markov model and incorporated the flow of uses between random access and scheduled access. And we have also evaluated the impact of schedulers and throughput. And the key takeaways are the random access and scheduled access throughputs depend on the number of RUs allocated for random access. And also the max throughput schedulers throughput depend on the number of RUs allocated for random access. And our work validates the need to model the variability in the number of users in random access and scheduled access. And some interesting avenues for future work would be the analysis of average access delay in random access and dynamic RU allocation policies in hybrid access OFDMA, where the number of RUs allocated for random access and scheduled access varies in consequent trigger frame cycle. Thank you.